So, welcome. New week, close to the end of the semester. Last week we discussed some stuff about inter-process communication, definitely, and we finished the synchronization topic of inter-process communication. So we compared the signal and wait method with locking and unlocking scheme. So with signal and wait, you remember maybe, we are able to specify the execution order of processes, of critical sections of processes, and by using locking or blocking and unlocking, we are able to just secure critical sections, so we don't care about the execution order when using this scheme. Next we jumped to the communication of processes, and we discussed the shared memory approach. You remember, shared memory processes are able to attach shared memory segments to their own virtual address space, and the shared memory method had one strong challenge or drawback, depending how you see it. Developers need to care about mutual exclusion. All other communication methods, here we have situations that the operating system takes care about mutual exclusion. So next we discussed the message queues. Message queues is also quite old inter-process communication method, and so we have two methods left. One is the pipes, and the other one are the sockets. So we start with pipes, and pipes are pretty simple way of inter-process communication, and to make it a little bit more challenging, we have two different sorts of pipes. So first we have the anonymous pipes, and next we have the named pipes. So we start with the anonymous ones because it's the older, I think, the older approach, and definitely the simpler approach. So anonymous pipes you can understand as some sort of a communication channel between two processes. It's a buffered one, and it's just in one direction, unidirectional. So if you want to be able to communicate in both directions between two processes, consequently you need two pipes. So pipes operate according to the FIFO principle. That's something you are well aware of. You know the FIFO principle well, and in literature, pipes are often just called FIFOs. The capacity of pipes is limited, so as consequence, if a pipe has no more free capacity and a process which wants to write on the pipe, wants to insert some data into the pipe, so the process is blocked. It's blocked by the operating system. And if a pipe has no data inside, if it's empty, and we have a process which tries to read from the pipe, so this process is blocked too. So also here the operating system will take care about this. The creation of an anonymous pipe is pretty simple. So we have a system call called pipe, and also a function call of the same name. So if you create a pipe, So you also get two handles, two file descriptors, which are used to access both channels of the pipe, so read and write channel. So inserting data or reading data from the pipe is just done with read and write system calls or library functions in the same way as accessing any data in files or so is done. So it's basically like working with a file. So anonymous pipes are a bit special compared to named pipes, because inter-process communication with anonymous pipes can only happen between processes which are closely related to each other, which means they need to be in a parent and child relationship. So that's a precondition. Otherwise, processes cannot access an anonymous pipe. Yes, they cannot get access to these handles. So it's a strong limitation. Yeah, if you have a situation in your source code, you create a child process and you want to do some interaction with the parent process, pipes are quite a convenient tool, anonymous pipes, but it cannot be used for any processes. If you want to learn about the pipes on your running Unix or Linux system, so it's pretty simple with tools like list open files, LSOF. So here you can get a list of all open files on your system, also the pipes definitely, and so you can limit the output like I did it here with the pipe symbol and the grep command line tool. So one special thing left, anonymous pipes are erased automatically by the operating system in case if the final process which has access to an anonymous pipe terminates. So because it makes no sense to keep the anonymous pipe any longer, because all other processes in the system will not be able to get access, probably. Yeah, as always in my course material, I like to give at least one example with source code, so just to see how people can play around with these things and use this for own software projects. So first here we have an example about a life cycle of an anonymous pipe, again in the programming language C, and it's not much, it's just 2 slides. And if you want to play around with this, or if you want to develop software with which uses pipes for communication, so with list open files, you already have learned this, you can monitor your pipes, and here with appropriate command line parameters you can specify what you are interested in, what information, and here we want to learn about pipes only, and we are just interested in the pipes which are opened by a specific process here. As alternative, you may just inspect the folder proc, so here you get real-time information about your system populated by the operating system kernel, and here we have a subfolder for every process. It's the same as the process ID, and here we have again a subfolder where we have file descriptors, and so we can learn about the file descriptors which are associated to this process, and so also we can learn about the anonymous pipes. So let's check the source code in detail. first we have some imports here of library, standard IO, standard library, and so we have the main function, and inside the main function here we specify some integer variables. One for the process ID of the child, it's the return value of fork, and here we have two variables for the handles. One for the read channel and one for the write channel. So next here in line 11 we try to create an anonymous pipe, and if the return value of this function, if it's not less than 0, so it definitely has worked. And so next we create a child process with fork. So if the return value of fork was less than 0, something stupid happened, no idea what. But if the return value of fork is bigger than 0, we are in the parent process. Sorry. So line 28 until 35 here, that's our parent process. The parent process will just inform us on command line about its own process ID, and next it will close the read channel of the anonymous pipe. It will insert, it will specify a string of called Textnachricht here, and this list, this character list here, character list, yeah, it's inserted into the anonymous pipe. It's written inside with the write function call. So with write here we specify the write channel, we specify what we want to place inside here, a pointer to the message variable here, and we need to specify the length, and so we calculate it on the fly with size of. Here we have the child process between line 38 and 47. It's specified again by the return value of fork. So now we are here in the child process, and the child process also informs us in command line about its own process ID. And next, the write channel is closed, and we specify in line 43 a receive buffer. We specify a maximum length of 80 bytes, 80 characters. And next in line 45 we read information, we read the message out of the read channel here, and we place it inside the buffer, and the required size, the length of the message here, it's also calculated here on the fly with size of. And finally we print out the message we have received from the pipe. We print it out on command line in line 46. So, and at the bottom of this slide, so we can see how to compile this and how to execute this. It's pretty straightforward as always when we use these C examples here. And so here we can see the output. It's not a big surprise what we get here. This example, the same as other examples from this slide set, you can find on the course webpage. It's maybe helpful for you if you want to develop similar things. So yeah, next we have the named pipes. Yeah, we don't want to to forget them. Named pipes are a bit more, they offer a bit more functionality, because we can use them for any processes, for inter-process communication of any processes inside the same operating system. So the named pipes are created basically like more or less equal as local files. So we have the function call make FIFO, and we specify a file name, and if it is required, also together with a path information and some permission, access permission specification. And so as consequence we get a file representation in the local file directory tree, and any process which has the required access privileges, the permissions to access this pipe, can use it for read and write operations. So the operating system again will take care about some mutual exclusion, and it's ensured that only a single process can access such a named pipe per time. And in contrast to the anonymous pipes, the named pipes are not erased automatically at any time, except if you switch off your computer. So we have a question. So the parent process and child process each has a pair of read and write anonymous pipe. If you want to exchange data in both directions in parallel, basically, yes. Yeah. So again, let's have an example. Yeah, it's not so much different to the anonymous pipe example, but it offers a bit more flexibility. Yeah, not only in the way of working with it, but also in the way of monitoring it. So again, here in the header of our C example, we import some libraries, and in the main function again we specify an integer variable for the return value of fork. And in line 11 things get interesting, because now we try to create the named pipe, and we do so with the function make FIFO, and we specify access privileges here. We specify read and write access privileges for all processes in the operating system instance here, and if the creation of the pipe was successful, so in line 19 the software here, the source code, tries to create a child process. So if it worked up to this position, we will have in the local directory, in the same directory where our executable is, we will find a file system record test FIFO. It's the same as the name we specified here in line 11, and so we can investigate this a little bit deeper if we check the file metadata, and here we can see at the very beginning of this line, the very beginning of the output here of ls minus la, so we can see it's the letter P, and this first letter here, it indicates it's not a normal file, it's not a directory, it's a named pipe. Yeah. So next in our source code, so next we have the parent process indicated here by the return code of fork, and the parent process will again inform us on command line what its PID is, and it will create an integer variable for the file descriptor for our handle. It's required to access the named pipe. Next here we have our data specified in the character list, and again it's the same message. And now with the function call open in line 36, we try to open this named pipe and write the message into it. No, sorry. First we just open it. Here we specify the name of the named pipe, and we specify also what we want to do here. We just want write access now, and next in line 39 with the write function, we specify what we want to write and where do we want to write. So the first parameter here, the first attribute, sets the file descriptor, our destination, it's a named pipe here. Next, a pointer to the message we specified and the size of the message. So finally, the parent process here will close the pipe, will close the file descriptor, and in the child process, that's not a big surprise what we do here. Again, we specify, we get informed about the process ID of the child process. An integer variable for the file descriptor is created. Again, we need a receive buffer. It's the same as we needed in the anonymous pipe example. Now we open the named pipe for read operation. So again, we do this with the open function call, and we specify now it's just read operation we want to do. In line 57, we try to read the data, try to read the string out of the named pipe. Here, destination, the file descriptor, the buffer where we want to write into the data we fetch out of we read out of the pipe, and the number of bytes calculated by the size of function. So, and finally we print out what we got on command line in line 58, and in line 61 we close the file descriptor, and finally in line 64 we try to get rid of the named pipe, we try to erase it. So it's done with the unlink function. If we compile this and execute this source code, we get an output similar like this. The only difference for sure is here the process IDs of parent and child, because yeah, it's dynamic. Yeah, it's offered by the operating system. The remaining stuff here, it's the same. If you want to learn about the behavior or existence, the state of your named pipes, you can use the same tools here and the same same locations in your file system tree. So you can use the lsof command line tool again, and here check the relevant subfolder of the proc directory, and you may also just check the named pipe in in the directory tree directly with ls and so. Yes, that's it about pipes. Pipes are not so advanced. Yeah, it's a pretty simple thing, a pretty simple way of inter-process communication, but fine for many situations if you don't have stronger demands. One approach is still missing. It's the sockets, and sockets are really different compared to the other inter-process communication ways, because sockets are the only option you have for inter-process communication across operating system boundaries. So sockets can use for inter-process communication inside a system, but it's also used for cross-system communication. So it's full duplex capable, so you can send and write by using the same sockets, and the way of interaction, I think it's pretty well known by most of you. I'm quite sure many of you have developed some stuff with sockets, and you also have discussed this probably in the computer networks course not long ago. So processes can request sockets from the operating system and use them for the exchange of data, and the operating system will keep track about the sockets and will keep track about the required socket information. So if you need to have socket-based communication, you also need to specify port numbers. Port numbers are the addresses of sockets. To be more precise, port numbers are the addresses on transport layer. And so port numbers address processes inside operating system instances. So we have some port numbers which are well known, which are specified, such so-called well-known port numbers. Examples are HTTP or SMTP for mail exchange, SSH or so. And you can implement sockets in a blocking and non-blocking way, in a synchronous and asynchronous way. So we have two groups of sockets, two sorts of sockets, and funny enough, you can use a single port number for two different sorts of sockets at the same time. So yeah, we can have connectionless sockets and connection-oriented sockets. It's pretty easy to remember if you compare it with real-life applications. So connectionless sockets, so-called datagram sockets, I hate the technical term datagram, I will tell you later why. Datagram sockets say use the UDP transport layer protocol. Maybe you have already learned in transport layer, yeah, between network layer and application layer we have the transport layer, and the transport layer has just two widely accepted protocols, two really popular protocols. It's TCP and UDP. UDP operates connectionless and TCP operates connection oriented. So UDP, fundamental technology of connectionless sockets, it is pretty lightweight. so we have lesser overhead compared to TCP, because no connection is established before information exchange happens. If you want to compare this with a real life application, best idea I have is when you send postcards from holiday, maybe. Okay, I know it's not so popular anymore, but maybe 1 or 2 times in your life you did so. Yeah, you send a postcard with a stamp and so really outdated thing. If you send a lot of postcards, you have no idea if they all arrive, and you have no idea about the order in which they arrive. Maybe probably it will be totally mixed. Yeah, you have no idea if the postcards arrive in the same quality as you did send them out. Maybe they will be damaged during passage. It probably happens. Yeah. And it's the same when we talk about UDP. Yeah, UDP information, UDP data, so-called UDP segments, they are sent out by the sender, and the sender has no idea if they arrive all, if they arrive in the correct order, if they are modified during sending. That's it. But it has less overhead, and sometimes that's exactly what you want. Best example I know, if you do live telephone, if you have a video call, yeah, because your boyfriend or girlfriend is doing an internship in New Zealand or Australia, I don't know, and you do these boring phone calls, so it's okay if you sometimes lose a frame, or if the sound quality drops or so, but you don't want lag situations, yeah, because frame is lost or some sound information is lost, and now the information is requested again, and this needs some time, and so the video stream hangs. And you also cannot work with buffers here, because if you operate with buffers, you lose the live the live situation, the live feeling. Yeah. So we get to the other option, the connection-oriented sockets. These operate with TCP, and in TCP, the other transport layer protocol, here we have the establishment of a communication first, of a connection first, and next information is exchanged by using this already existing connection. Benefit: nothing will get lost. Yeah, if parts of the transmission, if segments are lost, they are requested again. If segments are modified, TCP segments, so if they were destroyed basically or modified, they will be requested again, and so on. And the sequence, the correct sequence, is guaranteed. But we have more overhead compared to use UDP here, and we cannot use this for live communication like video calls or so. But maybe if you just want to stream a movie and you are happy with some buffers, so and you want best quality, or if you want to fetch information from a web page or email stuff, here you don't care about if you waste a little bit of time. You want everything in the correct way, so here TCP is perfect. Yeah, that's the main difference. So if you want to implement some stuff that uses sockets for inter-process communication, first it's a good idea because sockets basically can be used with every operating system, so it's very well portable, your software, probably, if you develop for socket-based communication. We need some functions for this socket-based communication. First, we have a function called socket for creating a socket, definitely. Next, we have some functions to make a socket ready, which means we want the operating system to assign a port number on sender side automatically. We want to create we just want to make it ready for transaction. We want to make the socket listening for incoming connection requests, maybe, and accept one of these, and for connection establishment, and so on. Next, we have some functions for exchanging messages, so for sending and receiving, and we have some functions for closing sockets. If you want to monitor your sockets on your local system, endless options exist. Two of them are you use a tool like netstat to list the sockets on your system, or again here with LSOF you can get information about the processes on your local systems that have sockets assigned. So again, we have some examples, and first here we look how the interaction is done in principle for UDP and TCP. So for UDP, first our processes both need to create a socket on local side. Next, the server process needs to bind a port number to the socket, and next immediately data exchange can happen. Yeah, it's connectionless, so exchange of data is done without connection establishment first. So we have the send to and receive from functions here, which are used, and finally the sockets will be closed. With TCP it's a little bit more advanced, so it's a little bit more challenging. So the very beginning is equal here, client and server, as I like to call them, despite it's wrong, because TCP does not differentiate, the protocol does not differentiate between client and server. In TCP, all communication partners are per definition equal to each other. So communication may happen in both directions, and no one is the boss, basically. But just to keep it a bit more simplified here, to keep it a bit more simple, I like to specify one process is client and one is server, and the one who binds the socket to a port number and does listen and accept is for me always the server. So yeah, first again, the processes create local sockets. One of them, the server, binds a port number to the socket, and this process also will make the socket ready for receiving by using the listen function. In detail, it means a waiting queue for connection requests is established, and so the process also specifies what is the number of connection requests which can be accepted here. And next, with the accept function, the server process will accept one will accept the first connection request in the waiting queue. So finally here the client will execute connect, and so the connection establishment is done. Next we have a connection established, and the exchange of data it occurs just by using send and receive functions, and finally the sockets are closed on both sides where our participants are, just with close. Let's investigate this a little bit deeper by using C. And now I need to apologize. I need to say sorry. Until last year, I had some Python source code here, Python source code examples. Python source code is always much more simple to read compared with C source code, according to my experience, and especially when we talk about computer network stuff, Python is a lot more simple than C. I came to the understanding that C source code is a lot better here now, because all other inter-process communication examples I have on my slide sets here are in C. So that's it. That was the motivation to modify this. Okay. First, we will discuss the server, which is used for UDP-based inter-process communication. For datagram socket data exchange. So first we have some header files specified, some libraries specified. Next we have our main function, and first we specify some variables, socket descriptor, and here address length. We specify a buffer, and we specify a structure here for the address. So it's C. So we need to override these pieces of our memory with 0 bytes. So otherwise we may run into C-related trouble. Next we specify what sort of protocol addresses we use here. Yeah, so we specify its IP based interaction on network layer, and we are willing to accept any sort of incoming requests. Yeah, finally here we have a position here for our port number, and here we specify the byte order. So next, in line 19, things get interesting. Here we create our socket with the socket function and the socket descriptor variable here. That's our way to access this socket now, and here we specify again the address type on network layer and the protocol on transport layer, datagram, so UDP. In line 20 we bind the socket to a process, and in line 21, sorry, we check the address length, and in line 22 we receive messages from the socket. We print out what we have received in line 24, and we will send back a message in line 26 with send to, and this message here is specified in line 25. So we will tell our communication partner, the client, we will tell him that we have received something. So on the right part here of this slide, we can see how to compile this source code and how to execute the server. So as command line parameter, we specify the port number, and yes, that's exactly what we read here in line 17. It's the first command line argument after the file name of the executable. So, and here we have the client source code. So the client source code is it has some strong similarities to the server code, because the very beginning here is equal. We create a socket in line 18 with the function call socket. We expect the user to print out a message on command line. We store this message and write it into a send buffer. We calculate the size, and we send this message in line 22 to the socket descriptor. So we will send it to the server. So we also receive the information from the server, the message that the server has received something, and we will print this out in line 27. And so again, on the right half we can see what happens. And so first we compile the client with the GNU-C compiler. We execute the file. We start the client process. We specify two command line parameters. The final one is the port number of the server, and the first command line parameter after the name of the executable, it's the network layer address. It's the IP address. Yeah, that's what we catched here. That's the IP address and that's the port number. So we are requested by the process to print out a message. It's done here, and on server side we can see here the server prints out the message it has received, and it sends back a string, "Oh, I have received something." So that's it for UDP. I understand at first sight it looks a bit strange, because it's a lot of source code for a little bit of features, but it's not so difficult to understand if you read it a second time maybe. Next we have TCP, and TCP, you remember, is a little bit more advanced. So on server side we have two additional functions, and on client side we have one additional function for the connection establishment. So on server side here we can see the very beginning is not different. Different is basically here in line 18. We specify our new socket we want to create now. It's a stream socket here, so it uses TCP. Next, in line 19, we bind the socket to the port number which has been specified, and this port number, yeah, here we have it. It's here we make our socket listening, so we specify the number of incoming connection requests. The maximum number, it's 5 here, and in line 22 we accept the first one with the accept function, and we read the message out of the socket and here we can see we use a file descriptor basically. Yeah, so here we have it, and we specify the buffer where the message will be stored, and we print it out in line 24, and we again specify a message which will be sent back to the client, and it's sent back in line 26 with the right function. And our file descriptor we used for read and write, and our socket descriptor we used for the listen bind and listen. We close them both, and that's it on server side. On client side it's not much different, so obviously again we create our socket with the socket function. We expect here the user to print out a message in line 21, and we will write this message into the socket. We will read a message out of the socket and print out the content of this buffer, so we will print out what we have received. Finally we close the socket, and here on the right side we can see we compile the client, we execute the client with two command line arguments, again with the network layer address and the transport layer address, so the IP address and the port number. We print out a message, and on server side here we get the information what message has been transferred, and on client side the message from the server is printed out, so it's just an indicator, oh, he got something. Yeah, it's not so difficult. It's not so difficult if you have seen it at least one time, and if you have played around a little bit at least one time. Yeah, time for a summary of the different sorts of inter-process communication what we have discussed so far. So we had the shared memory, we had the message queues, we had the different sorts of pipes, and we have the sockets. Basically everything is memory based except the sockets. Sockets are message based. No, sorry, that was totally wrong what I told you. Everything is basically message based except the shared memory approach, that's memory based, sorry. Next, the limitations in regard of the directions. We have shared memory, it can be used in both directions. Message queues and pipes not really, not at the same time, and sockets can be used in both directions at the same time. In platform independence is given just with sockets, because sockets can be used for inter-process communication across operating system boundaries. And do we need a relationship, a close relationship between processes only for anonymous pipes? That's a precondition. For all other sorts, not. Next, what about the data structures and the data inside? Is it kept by the operating system without a bound process? And that's not given for shared memory. Sorry, that's not given for anonymous pipes. And it's also not given for sockets, definitely. Yeah, and the synchronization, who cares about synchronization? Who cares about mutual exclusion? It's given everywhere, automatic mutual exclusion implemented by the operating system, except for shared memory. Yeah. So as consequence, shared memory looks a little bit outdated, or a little, or it has many strong limitations, obviously, but it's not obsolete. Yeah, you can use it. You can implement it for many interesting situations, and yeah, it's good for the moment here. That's enough for different inter-process communication methods. So one thing is left. One big topic is left about inter-process communication. So we had the synchronization factor, which was elementary. We had the communication schemes, different methods of inter-process communication, and one thing is left. It's the cooperation. So cooperation means we have shared resource usage. Yeah, we have common data maybe, and how can we implement it that several processes use this common data, these common resources. So we have two basic approaches here, two basic technologies which can be used. It's semaphores and mutexes. Spoiler alert, semaphores are better. I will explain why. So a semaphore is basically, I want to explain it as simple as possible, it's basically a counter lock variable. So it's used to protect, it's used to lock critical sections of processes. Semaphores are pretty old. The concept of semaphores is pretty old. So it's from the 60s, 1960s, and it was implemented by a living legend of computer science, by Mr. Dijkstra himself. So nice to read if you enjoy such things. One of the literature references where Mr. Dijkstra explains what semaphores are, probably first, yeah, a publication from the 60s. You can download it freely. Interesting to see how things developed in the last decades. So not much in regard of semaphores, honestly. So a semaphore, I told you, it's a counter lock variable. Here we call it S, and it has we have two operations which are executed to modify this counter lock. It's the P operation and the V operation, and it's a stupid naming at first sight, but maybe not so much if we understand what the origin of these names are. Mr. Dijkstra was from the Netherlands, and so the P operation, it comes from the Dutch word which says we try. We try to reduce the value of this counter lock variable, and the V operation name comes from a Dutch word which says we want to increment this counter lock value. The operating system ensures that these operations are atomic, so they cannot be interrupted by other processes. That's a strong precondition so that we can have mutual exclusion. Another thing which is relevant, these counter locks can be used to allow several processes to entry their critical sections. Yeah, it's not only used, or it it's not limited to single processes. If you are happy just with single processes going into the critical section, then you can use a mutex. But if you want the feature of counting, so you need a semaphore. Yeah, so we have two data structures for semaphore implementation on operating system side. So first we have the counter variable. It's an integer one and it's non-negative. So it specifies how many processes can cross the boundary to the critical section, can cross the counter log variable before the address space is depleted, yeah, before the log value is 0. And next, in the operating system, we have a waiting queue. We call it here the waiting room for processes. So processes are in state blocked inside if they wait until they can pass the counter log variable, until they can pass the semaphore and access their critical section. So first, if you want to work with semaphores, you need to initialize a semaphore with an initial value. That's the maximum number of processes which can be inside the critical section. And next, the P operation will check can the semaphore value be reduced. Yeah, is it bigger than 0 or is it already 0? If it's bigger than 0, it's reduced by 1. If it's already 0, the process which tried to execute the P operation is blocked and is transferred to the waiting room, to this waiting queue, and so here it waits for the operating system to release it. And next, the V operation means the semaphore value is immediately incremented by 1, and if we have at least one process in the waiting room waiting, so the first one probably is deblocked and may continue with its P operation. So now we need an example. Why the hell should we use semaphores in real life? And there's one example which is used probably since decades to torture computer science students. So they need to understand or they need to learn why they need semaphores now. It's the famous producer-consumer example. So in this scenario, we have a producer process and we have at least one consumer process. The producer creates data, packets of data, and the consumer is doing whatever with these data. Yeah, I don't care. We have no idea about the performance of these processes. Maybe the producer is quite fast, maybe the consumer is quite fast, I don't know. We have no idea about the scheduling. So if the consumer is working and the producer has some data created, consumer cannot handle it maybe, and in the other direction, if the producer is too slow, maybe the consumer is needs to wait all the time. And so it's a good idea, it's a smart decision to have a buffer. The buffer has a given capacity, maximum capacity. Nothing is unlimited in life. And so the producer will store its data in the buffer, and the consumer may fetch data from the buffer. So if the buffer has no more free capacity, consumer must be blocked by the operating system, and if the buffer is depleted, if it has no data inside, the consumer need to be blocked by the operating system. Truly critical, truly mandatory is that we have atomic operations here. Yeah, P and all access operations to the buffer need to be atomic, and that's given. Yes, that's implemented by the operating system. If you want to understand better what can go wrong here or what happens here, I really like this image. I stole it from this guy here from the United States. When I understand it right, he's a professor too, a colleague of mine, and one of his students did draw this picture. My students never draw such nice pictures, I'm sorry. So I needed to steal it. It explains well, a graphic example here, it explains well the producer-consumer example. And the problem here is mapped to a pub situation. So we have a producer here where beer is filled into mugs, and we have the consumers here. It's the guests. We have one guest here, one producer, one guest. The number of mugs is not infinite. Yeah, it's a given number. Oh, here it says infinite number of mugs. Sorry, but the buffer is limited. Yeah, the mugs are unlimited, but the buffer not. It's the size of the bar probably. So the buffer here works well. The consumer consumes well. Everything fine. But here we are running into trouble. The consumer took a record, took an entry, took a mug from the buffer before the producer was finished. That's bad. So how to solve it? Fill in? Yeah, definitely by a semaphore. Yeah, we want to make sure that that records which have not been finished, they cannot be removed by any process. So we need at least one semaphore here to protect records which are not truly available now. And here next image, the consumer waits for the producer because here we are running out of data, we are running out of filled mugs, and so the consumer is blocked. And here we have the other situations. The consumer cannot consume fast enough. Here he went to the washroom. The buffer is filled, and so the producer need to wait. If the consumer is busy, can consume, the producer must wait if the buffer is full for the consumer to start consuming again. The process is now fill in. Yeah, it's blocked, definitely. Okay, so now we still have this bloody producer-consumer example. How to do this? How to implement something like this? A simple question: how many semaphores do we need? Many people would say 1, and that's wrong. We need 3. We need one semaphore that takes care about the filled mugs. Sorry, no, we are not talking about mugs anymore. The filled locations in the buffer. Yeah? We need one semaphore to take care about the empty positions in the buffer, and we need one semaphore just for the mutual exclusion. So the first semaphore filled here, it will count the number of occupied locations in the buffer. It's incremented by the producer and it's decremented by the consumer. So if the buffer is empty, so if filled is equal to 0, consumer is blocked. And empty, this semaphore counts the available buffer locations. It's decremented by the producer and incremented by the consumer. So if it's 0, the buffer is has no more free capacity, and so the producer is blocked. Yeah, and the final semaphore, I call it mutex for a reason. Yeah, just for the mutual exclusion. It's state of the art to call it this way, because we don't need any counting feature here. We just want to make sure we have mutual exclusion. So mutex, it has value 0 or 1 here. Such semaphores like mutex here, they are also called in literature binary semaphores, yeah, because here we just ensure mutual exclusion between two processes. This example is a little bit special because the solution I provide here is just pseudocode, yeah, for reasons of size. Just I did not want to invest here 10 slides or so. It's just a single slide now with pseudocode, but I will show you another example about semaphores in a few moments, and so it's good enough here to have pseudocode. First, we specify the initial values of our semaphores, and filled initially is 0 because we have nothing in the buffer at the very beginning. Empty is 8, that's our capacity of the buffer, and mutex is 1. So we just do mutual exclusion here, and we specify which process, consumer or producer, will run first. So we have two processes here running in infinite loops, the producer process and the consumer process. The producer process will create some data. I don't know how, maybe it's just random, pseudo-random data, or I don't know. We don't care, it's just any data created. Next, our producer process, it will try to decrement the semaphore empty. That's possible because it's bigger than 0. It has value 8 at first place, and so it can be decremented. Next, our process will try to decrement mutex, and that's possible too, because initially it has value 1, and so here our process can reach the critical section and can insert a piece of data inside the buffer. So next, the process leaves the critical section with by raising the mutex semaphore by incrementing it, and next it increments the semaphore filled, because now we have one record inside the buffer which can be removed by a consumer process. So, and the consumer process, maybe we have many consumer processes, but a consumer process will check can the semaphore filled be decremented with the P operation. Initially it cannot, but after at least a single producer run it can. So mutex need to be decremented too, and so the consumer can access the critical section and remove a record from the buffer, and next the mutex variable is incremented again, and the semaphore empty is also incremented by 1. So, and next, the consumer need to do something with these fine data. I don't know what. Maybe it's stored somewhere or printed out or further handled. I don't care. Yeah. So, summary. Yeah. With these 3 semaphores, we ensure mutual exclusion, and we keep sure that the buffer will never, we have no overfill situation, and consumer processes are blocked if nothing is available to become consumed. What's state of the art now? What's the situation now in Linux? Or yeah, it's a little bit different compared to the Dijkstra concept, which is more than 5 decades old. But it's not a strong modification, honestly. Today we have groups of semaphores. Yeah. Okay, you can also specify a group of semaphores which just has a single semaphore, which is probably done quite often, but you can also have many semaphores in a group, and you can execute P and V operations for entire groups of semaphores. So you can ensure that only if all semaphores in the group maybe can be decremented by the P operation, so all processes or the process which wants to do this summed up operation may continue. So these things can be done in an atomic way. It gives you a little bit more flexibility compared with the concept of Dijkstra. Yeah. The operating system kernel will also maintains a semaphore table now with referencing to these groups, and for every semaphore group, so here we have an array where we have the individual semaphores, their addresses inside. We have 2 different sorts of implementing semaphores, and here it's basically the same as we had when we talked about shared memory and message queues and so on. We have the System 5 approach, the old-fashioned one, and we have a POSIX approach. So we can use the implementation of the kernel basically, or we can use the implementation of the POSIX library, which is a little bit more modern and better portable, but System 5 is, according to my experience, yeah, I consider it as quite simple. Yeah. So we have just 3 system calls or function calls of the same name if you want to do System 5 semaphore stuff. So we have samget for the creation or opening of existing semaphores or groups of semaphores. We have samcontrol if you want to modify a semaphore or group of semaphores, or if you want to get rid of it, maybe if you want to erase it. We have samoperation for carrying out P and V operations on semaphores or groups of semaphores. And if you want to learn about the state of your semaphores on your system, you have again the command line tool IPCS, which we had last week. So here we have one example, and yeah, I told you such examples are always several slides. Yeah, so here it's 5 slides. I'm sorry, but we are getting closer and closer to the end, so it's yeah, you will survive this. This example is also, yeah, it's always difficult to say. It's pretty simple, yeah. It shows a little bit how the life cycle of semaphores is, yeah, and how to do some semaphore related stuff. Many lines explain short, yeah. Our example here will create a child process with fork, definitely, and so the parent process and the child process both want to print out single characters on command line, and we don't want the same characters one after the other. So we want one process to execute a character, to print out a character, send the next process, send the first process, next process, first process, next process, and so on. So we want mutual exclusion, and the critical resource here is the command line, where we want to print out characters. So the very beginning is always quite simple. Here we do some includes of function libraries. Next we have our main function, and we specify some integer variables. One for the fork return value. We specify semaphore keys, and we specify some variables for further return values we need to store. Yeah, and finally here we have one for the output. So this set buffer is a bit of a hack. Yeah, we don't want any buffering of standard I/O of the command line interface, which is enabled per default today. We want no modification by the command line tool of our output. So otherwise it's hard to find out if everything runs well. So we don't want the output to become modified. So next we create one semaphore group here with semget function call in line 19, and we specify this semaphore group has just a single semaphore inside, and we want to create a new group. We don't want to access an already existing one if it exists with the same name. Name is specified here, 1, 2, 3, 4, 5, and we specify the access privileges. So next we try to create a second semaphore group, again with semaphore get in line 26, and it has the key, the name 5, 4, 4, 3, 2, 1. Sorry, it's a stupid naming, but it's sufficient. The group has just a single semaphore inside, and it's the same parameters here. Next we specify two structures here. For P operation and V operation we specify what this means in detail, and it means P operation we want to decrement a semaphore, and V operation we want to increment it. So next we specify the initial values of the semaphores. We just have one semaphore in each group. Initial value of semaphore group 1 is value 1, and the initial value of the semaphore in group 2 is value 0. So in line 46 and 50 we fetch these values just to give you a good show, yeah, and just to demonstrate to you how this can be done. And in line 47 and 51 we print out these initial values just for show purposes and debugging purposes. So next we create a child process in line 53 with fork, definitely, And in line 56, the child process starts. The child process happens here, and here we have we have a for loop, and it will loop 5 times, and so it will print out the letter B, but only it will print it out 1 time, but only after we can do the P operation in line 58 with SEM_op. We can reduce, only after we can reduce the semaphore, the first semaphore in the second semaphore group by value 1. Execute the P operation. If it can be done, B is printed out. That's the critical section. We wait for a second, and next we increment the first semaphore in the first semaphore group. And the parallel process will basically do the same, but in the reverse order. It will loop 5 times, and it tries to reach the critical section by incrementing, decrementing the first semaphore in the first semaphore group, P operation, and print out letter A, wait for a second, and increments. Next, it increments the first semaphore in the second semaphore group. It increments by 1. So that's the main feature of our program. Yeah. Next, we will wait until we will wait until the child process has been terminated, and we try to erase our semaphore groups with SEM control. In line 85 and 94, we try to remove SEM, remove ID. We provide here the return codes of SEM_get, return values of the SEM_get function, and so we probably can get rid of these groups. So if we compile this with the GNU-C compiler and execute it, we will get an output like this one here. We can see the semaphores are created, they get initial values. We get this string printed out here. It's these letters, one after the other, A, B, A, B, A, B. The first letter is specified by the initial values of the semaphores, and so we have no groups of A's or B's in a row. Finally, we get rid of our semaphores here. IPCS will tell us about the semaphores, so here we can check if they really exist. Yeah. And so we can check the permissions and the ownership and the number of semaphores per group. And here, by converting the keys from hexadecimal into decimal notation, we can double check if everything went right. So yeah, without the mutual exclusion, we would have outputs like this one, yeah, with sequences of A's and B's, and without semaphores at all, we would have sequences like this one, depending on the execution order, child first or parent process first, and in seldom cases maybe we could observe here the process switching done by the operating system, maybe because of scheduling events. Oh, stupid thing, we are so close to the end but have not yet reached it. But final words about semaphores, come on. yeah, the semaphores, you can, if you need to implement something with semaphores, you can use the System 5 semaphore way. In my opinion, it's the most simple one, but you can also use POSIX functions, the POSIX library. Yeah, some people favor one or the other way. I cannot tell you what is best. In the POSIX way, you have more flexibility. Yeah, you have blocking and non-blocking operations here. You can also specify timeouts and when they expire, or if not. So it's a little bit more flexible, and the POSIX semaphores, they are created here in this subfolder, dev shared memory. They are inside with the name semaphore dot and the name you specified, and so you can monitor this pretty well. I have no example about POSIX semaphores in my slide set, but it's on the course webpage. Okay, super short summary about mutexes. Mutexes are basically castrated semaphores. Yeah, so if you don't want the counting feature more than value 1, so if you are happy to basically differentiate two states, you could use mutexes. A mutex is just for handling two states. It's basically the same as a binary semaphore. Stupid thing, there is not just one mutex implementation. Yeah, you have several implementations. You have the standard library mutexes, you have the POSIX thread library mutexes, you have the C standard library mutex from Solaris, which is dying out slowly. Mutexes are pretty well suited if you just wanna have mutual exclusion between threads, the threads of a single process. For inter-process synchronization, it's not always suited. Yeah, it could be used when using System 5 or POSIX, but then you need to go you need to use an additional shared memory segment, and that's it's not nice to program with these things. Honestly, I never enjoyed using mutexes, and it was never really required for me. Yeah, if I need a lock variable feature, I always use semaphores, and I'm happy with it. I don't like mixing concepts, and semaphores are just more flexible. So yeah, final slide. If you want to implement stuff with shared memory segments, message queues, semaphores, and if you are happy to do the System 5 way, to go the System 5 way, there's one tool which is really important for you. It was the IPCM for monitoring, but also there's a second tool, IPCRM, because if you implement programs and sometimes you forget to erase such resources, and or your application crashed and the message queues or shared memory segments are still available, and you want to remove them by hand, you can do so with IPCRM with this command line tool. It will not help you if you go the POSIX way, but if you go the POSIX way, you can just erase these resources by hand if you inspect the relevant subfolders in your file system tree. Yeah, in the folder devices shared memory and devices message queue. Here you can find these segments, shared memory segments and semaphores and the message queues, and can erase them just with the rm remove command. So that's it. Wow, you survived the inter-process communication. It's a big bunch of information, I know. Do you have some questions? I have one question here. The question is why we were talking about TCP and UDP too. Yeah, UDP and TCP, so sockets can also be used for inter-process communication inside one system, and it's heavily used for this purpose. Yeah, you don't need to go across a real computer network. You can also just use it for communication of processes inside one single operating system instance. Why not? It gives you the freedom to have both options, yeah, across a computer network or just inside an operating system. No more questions? Okay. Okay, I see. I finished you. You have another question. Okay. We have some minutes left, no problem. I will stop the recording, and so we will discuss the remaining stuff.